Okay, so this is my final presentation. So I used data from Kaggle. It was Airbnb data basically from the past year. It had a ton of information about the price of rentals. Um, it was originally used to create this website that I took a screenshot of to predict the price in different regions of the US. So my goal was to attempt to predict the rental price. So if somebody were to potentially invest in buying a house to rent on Airbnb, they would have a better idea of what they were getting into. I was hoping to be able to predict the price, but I also wanted to look at how the different features affected the overall price. So, location, there's a bunch of different cities. There's Boston, there's Chicago. If I were to buy a house in Boston to rent out, would I be able to make more money? Um, Number of reviews. Also, I wanted to know if that affected the price, minimum nights. So if I have to have a minimum night of one, will that affect it? And the number of booked out of a year, do I need to have the whole entire house rented for the entire year in order to make any money? So I looked at the distribution, the correlation, identified outliers, and prepared data with the correct class. There was a lot to do with this data set. As I said, there was a lot of different features to play around with. This is just a screenshot of one of the things I did. So you can see the price was skewed to the left a little bit. I was able to replace it with the mean, and you can see there's much better distribution. Still a little bit left skew, but not too bad. So transformation was performed. I was able to transform. For my multiple regression, I did dummy code for the city and the room type. For my logistic regression, I made the price categorical, and for my decision tree, there wasn't much to do, mostly because I had already done everything there would be, and also because decision trees are just versatile. They don't really need specific variables like that. So here's just a quick look at my code and how I converted some of those variables. So as you can see, room type for my data frame and city is one column. So by running my code right here, converts all the private and shared, and then this one converts the cities. You can look back at my data, and now I have all of them put into different binary categories. Let's see, did I not run this code? Oh, it's right here. Perfect. One thing to know about the data is, so there was private room, shared room, entire home, and other. Obviously, there's going to always be that third one that's left out. So Hawaii was left out and other was left out. So for my multiple regression, so the reason I chose multiple regression because it is good at predicting continuous variables, and I was really interested in getting like an exact price prediction. Um, and it also tells you a lot about the different types of variables, which, as I said previously, I was very interested in not just the price, but like how the different variables affected the data. And I was actually able to see that minimum nights and number of reviews had like a very large impact, more than the city or the type of room, which was surprising to me. I would have thought that people would prefer a private room more than they would prefer the city, but I guess not. My second model was logistic regression. I did this because I thought it would be a good comparison to the multiple regression, and it's efficient with training. Unfortunately, it's not really good with large features, so that was kind of a downside. I think there was a little bit of overfitting, but it was really nice to be able to compare the multiple regression to the logistic regression. Decision tree, I chose this because I thought it would be nice to I chose this because it's a very versatile model. It's good with both categorical and continuous variables, and it was actually the most accurate out of all of the models. So multiple regression was evaluated by RMSE and 95% confidence interval. Linear regression was evaluated with the ROC and the AUC. And decision tree, I use the confusion matrix, and I'll show you the code. This is just the ROC of the linear regression and the final chi-squared or confusion matrix of the decision tree. So for the multiple regression, as I said, I looked at the mean squared error and the confidence interval. I also just compared the test data with the model right here, so you can see some of the data is fairly accurate. So you have 72 and 60. It's pretty close price, but then some of the data was way off, almost double what the actual price was, or half in some cases. So that was really interesting. Some of them were close, some of them weren't. So then when I was looking at the root mean squared error, this is very high, showing that the model was not that accurate. Again, if you look at the 95% confidence interval, it's very large. This model was not that accurate. Again, I like that it showed exact predicted price, but the confidence interval and the RMSE were just not what you would want them to be. So when looking at the linear regression, I plotted the ROC and found the AUC value. So this is a pretty nice curve, actually, which was nice. And the AUC was 72. So the accuracy is about 72. That's pretty accurate. This was a nice model. The only downside to this was that the breaking up into the two different variables, but I'll get to that later. Decision tree was determined by the confusion matrix accuracy. So if I run that, so everyone knows what the accuracy is, the true positive plus the true negatives divided by the total. So it ended up being around 80%, which is the most accurate model. The ensemble models that were built, so multiple regression and linear both use backfitting for their ensemble models. So it was built by backfitting. The features just became statistically significant, but that actually didn't improve the R mean squared or the F statistic or anything. For multiple regression, linear regression, the AIC actually did get lower across 3 models, so that did show that it was improving as the insignificant features were removed. And then the decision tree, we used boosting, and that improved the accuracy of the model from 77 to 80%. But it did not improve between the second and third model at all. It stayed at 80. The only thing that changed was the true negatives and the true positives flipped. So this would depend on if you want to be for sure that the model is expensive, or be for sure that, or the rental is expensive, or be for sure that the rental is going to be cheap. So overall, multiple regression predicted the exact price, but it was the least accurate out of all the models. Logistic regression was accurate. However, I had to split the data into cheap and expensive, which left me to decide. It was a huge range. So it was really good at predicting, but it was only really good at predicting it'll be cheap. Okay, it'll be $0 to $200. So the range was large there. And then decision tree was the most accurate, but it didn't really provide any information that I found useful. It just told me that like it was likely to be this or likely to be that. So that is why I think logistic regression was the best fit for what I was trying to look at. Um, I can see improvements in this model by adding more factors than just cheap and expensive. So instead of having just, two different variables, maybe we could have cheap, moderate, and then expensive, and that can actually give me more information as to what I should price my potential rental or what price my rental should be in. But because it was a mixture of accurate and informative, I think that logistic out of these three was the best model to use.